we'll talk about diversity and equality in social networks. Ana is a PhD candidate at Columbia University. Her work focuses on mathematical models, data analysis, and inequality in social networks. From recommendation algorithms to the way information spreads in networks, Ana is particularly interested in studying the effect of algorithms on people's sense of privacy, community, and access to information and opportunities. She strives to integrate tools from mathematical models, from graph theory to opinion dynamics, with sociology to gain a deeper understanding of the ethics and implications of technology in our everyday lives. Ana grew up in Bucharest, Romania, and she moved to the US for college, where she graduated from Princeton in 2016 with a bachelor's degree in mathematics. Since 2019, she has been co-organizing the Mechanism Design for Social Good initiative. The floor is yours, Ana.
Thank you so much, Aida, and thank you everyone for inviting me. I'm really excited to talk a little bit about my research, and let me start sharing my screen right now. All right, I think you should be able to see my screen now. Right, so as Aida said, I'm a PhD student at Columbia. I work with Augustine Chantreux on issues related to diversity and inequality in social networks. And I wanted to talk a little bit about a couple of projects today, as much as we have time for that. So to get started, there's the issue of inequality that relates to a bunch of different applications in society, from the way like we get access to education, to technology, to different products, to job opportunities, and so on. And a big correlation is how our social network actually influences this kind of access. So who do you know really matters? And that can reflect in your community, who is connected to you, who can provide you support for that, the kind of products you have, and the way you can communicate to people through it. And more recently, a lot of that moves into the online realm as well. So what groups are you in? Who are you again connected to? And how does information flow get to you as well? Which affects again the kind of jobs you can get and the general access to different opportunities you may have. So there's different applications to that in which like nowadays more and more algorithms are being used to influence this this access, and the way they interact with the structures that are present in our networks really matters as well. So the main questions I want to ask is like, what is the role of social networks in creating and perpetuating inequality? And in relation to how algorithms are being used, that relates oftentimes to having a graph in which that represents our network, in which there are different communities that are connected differently. And the question is like, how do we assess and fix like biased outcomes? And the very definition of what is a biased outcome depends on the applications that we're looking at. So for example, if you're trying to diffuse a message in a network, you may look at a pattern of who does not receive the message itself. If you're trying to like recommend people to connect to each other or provide recommendations for different items, you may again look at who does not receive like good recommendations, or whether there's a pattern to people not receiving recommendations as well. So these are the main topics that I'm like focusing mostly in my work on, like recommendation, information diffusion that I've mentioned, the problem of social influence. And there's other applications like in districting and gerrymandering that I'm not going to really talk about, but just mentioning here. And there are many other applications to it as well. So I'm going to mostly focus on this information diffusion case as one that's like really relevant. It's a recent project, but I'll quickly touch on the others as well. So the problem of information diffusion is defined through this like technical problem of like social influence, in which you have a network and you are the information flows through it. So whenever someone gets a message, they diffuse it to their friends, who diffuse it to their friends, and this process continues into a cascade. And oftentimes you have a central actor who's trying to give information to as many people as possible. Like think of, for example, like healthcare guidelines during COVID, or information about vaccination, or like things like that. And oftentimes there's like, you can't really give that information personally to everyone. So you're going to choose a set of early adopters, your seeds, your like campaign that you're starting with, and rely on them to spread the information as well as possible in trying to maximize the overall outreach. And this is formulated through an optimization problem based on the constraints of how big of a campaign can you actually run, do you have the budget for, and the model through which like people diffuse information with. This problem is hard, it's NP-complete, and there's been several algorithms to try to solve it that are based on, choosing people who are very central in the network. If you choose people who are more on the periphery of it, you might not have a successful way of actually diffusing to as many people as possible. But if you choose people who are central, several algorithms have been shown to show that as being successful. So for example, choosing people on the number of connections they have, on other measures of centrality, like distance centrality. Also iteratively through greedy methods. That's a method that works, is provably quite close to the optimal one, but it's very computationally expensive. So what happens, however, when you have different communities that connect differently with each other is that you may end up continuing to advantage people who are already very central in the network itself. And it has been shown through recent works that bias in the centrality measure and social structure actually gets reproduced. I know a lot of you here have also worked on this problem, and it's been really inspiring for me to read on that. And the question is, what do we do about it, right? So there's different interventions that we can think about to make sure that the different groups that are present in the network are also represented in the outreach. So you're not leaving communities out of the loop. One of the methods is what Lily was also saying, based on this classical methods based on fairness definitions in machine learning that relies on statistical parity. So for example, if you're trying to achieve the statistical parity in an outreach to make sure each community is as represented as the general population, you may do that as posing it as a constraint in the optimization function. For example, if you're using a greedy algorithm. So you're trying to represent each community as they are in the general society. And that ends up with a trade-off between being fair and being efficient. And here what that trade-off means is that if you don't think about that constraint and you just rely on the network and your traditional algorithms to diffuse information, you end up with an outreach. And it may be pretty good depending on what algorithm you use. If you're adding that constraint at the level of outreach, you may be more diverse, but you're going to reach fewer people. And this is what this fairness efficiency trade-off looks at. In this work, we wanted to take this different approach when we're looking at partially known networks in which greedy algorithm is hard to use, but we're using other centrality measures like number of connections, in which we're also using the model of network growth and trying to detect and tap into inactive communities. And that leads to actually we're able to study in which conditions can you actually be more fair and more efficient at the same time. And that condition really depends on the size of your campaign. And it's illustrative through this model to understand where this trade-off occurs, when it doesn't, and what we can do about it. So I'm going to spend a couple of minutes just talking about that result. And the main idea is, as I mentioned, this is a project with our collaborator, Jesse Shinihan, and my advisor, Augustine, from last year. And the idea is to tap into inactive communities in the early adopter set. So if you're thinking about a baseline algorithm that ignores labels, ignores community affiliation, just relies on basic centrality measures as we've done before, that's agnostic. And that's seeding the network in an agnostic manner. And it may end up with the outreach that we're expecting it to get. The proposed heuristics that are trying to change that are, we call them both parity seeding and diversity seeding, and both of them are trying to ensure parity, statistical parity in the campaign itself. And that may mean that you're choosing less connected people than you would if you don't think about this. So a small difference is that, parity seeding tries to enforce a strict condition on statistical parity in the early adopters, while diversity is a relaxed version of that. So it's always going to do a little bit better in the terms of outreach. So what happens with this is that we wanted to compare how these heuristics behave with each other for different networks. And just to quickly remind that this can be turned again into an optimization function that has a different formulation to it, in which we can use a model to try to solve it and understand exactly where the trade-off occurs. All right, so I want to show you one plot of how this actually ends up looking. And this is based on a simulation on a variety of networks that are based on the real data that we also use to validate these results. And these networks look, and this set of simulated networks look in the following way. So on the x-axis, we're looking at how unequal your network is. from 0.1, that means you have 10% minority. Let's call that like red, and the majority, let's say it has blue label. And a quick note here, that can mean like, these communities can mean like demographics, it can mean like political affiliation, interest groups, or anything else. And as we move towards the right, we get to more and more equal networks, where like 0.45 means you have 45% of the minority group in red. And this is a network that's generally about like 53,000 nodes with 2 communities and some level of homophily, which is what we notice in the real data as well. So people who are similar, of the same label, tend to connect more with each other. On the y-axis is the seed set size, the size of your initial campaign that you're trying to like use to diffuse information. And of course, if your budget is high and you can use a large campaign, you're going to do better in diffusing that information. But that depends on what the budget is. And what we see is that in the different colors is when exactly does the baseline perform the best in terms of outreach, and when these diversity interventions perform better. So in orange is the region where like not being diverse at all actually performs the best. And otherwise, there's like a small trade-off between being fair, doing diversity or parity seeding, or being agnostic. In the blue and purple regions are when we actually, the seed set size is big enough that we don't have a trade-off anymore. So both for the blue region, diversity, a relaxed version of statistical parity, is able to perform better. And for the purple region, that's where also a strict parity condition also performs better than the agnostic version of it. So I'm gonna like speed through to make sure that I'm not out of time. But what we see is that, of course, for networks that are more equal, these diversity interventions start to perform better and better. And there is a large amount of like parameter cases in which you do not actually get a trade-off. And the theory behind it is based on this like network model of growth that gives you an analytical condition exactly when do you get a trade-off and when do you not get a trade-off. And I'm going to give like a very quick overview of how this model works. So this model is based on a biased preferential attachment in which you have 2 communities, the majority and the minority. They connect with in a preferential attachment way, which creates this rich get richer effect. And there's homophily as well, which we see in the data sets that we use as well. I didn't mention that in the previous case. These results are really consistent with the data that we use. We use some data from Instagram and from DBLP with like large networks to try to diffuse information through them as well. So what happens with this model is that we know that this model actually exhibits inequality in the degree distribution of the 2 communities. And we're able to use that in order to show that, to show exactly, to formulate the analytical condition for which like running a campaign that's more diverse can actually perform better. This model is particularly useful for other applications as well. And we're using this model to augment it with recommendations to see what happens if instead of trying to diffuse information, you're trying to like give recommendations to people. And this is a project that it's actually preceding this project, but it's with Chris Ritter and my advisor, Augustine. And what we see in this project is that, well, there is inequality at the level of degree distribution if you think of this like organic growth of network. And if you add recommendations that are often used in like friends of friends recommendations, so here we're looking at the random walk of length 2, what we find is really interesting. And we find that in the social influence case, you can really fix it quickly to not get a trade-off between being efficient and being fair. In this case, the adding recommendations just makes things worse than before. So what I mean by that is that the initial inequality we saw in this degree distribution at the level of this power law between the 2 communities actually gets worse when you add friends of friends recommendation. So the differences get exacerbated. So there is this trade-off that you get between having these recommendations that are like generally good and trying to be more diverse in this. So this is a case where like inequality in the network actually gets worse, and we see that with the data sets that we use again on DBLP and Instagram as well. So I think I'm gonna stop here because I don't want to go too much over time. But I think Lily really made a good point about like, these fairness conditions have limitations as well. And it's really important to think about like what's the social welfare aspect of these problems as well, and what other definitions are more helpful in order to provide better interventions for the work that we're trying to do. And to finish on that note, this is a work that with collaborators who I know some of you are here with Jesse Rowland, Fedra, Gurab, Manish, and Stratis from this year from FAC, trying to really pinpoint what are different definitions from different fields that we can bring together in order to tackle this problem. So from machine learning and from mechanism designs, we talk about different lessons that we can learn in terms of like the tension that Lily mentioned about welfare and fairness, long-term effects of fairness, and the fact that people can be strategics, as well as like other things we can learn from the machine learning definitions that we were looking at, like group level diagnosis and the plethora of definitions that lead us to thinking differently about what exactly are we defining to do. So I'm going to stop here. Sorry for taking too long, but thank you so much for the time, and I'm looking forward to your questions.